Hey guys. So I'm going to try this a little bit differently this time, with a little bit of different software because a few of you guys had some errors with the last lecture file. The videos weren't playing well. So we're going to try and troubleshoot this out, and if I have to, I can re-record the old ones in this one. So hopefully one of these versions will help. So to that end, before we even get started, if you're watching this and you're getting video, great. Please let me know if you were having a problem and this has now fixed the problem. If you are seeing me as if I'm not talking right now, then you probably have no clue what I'm saying. So I'll post something to Canvas and hopefully you can tell me then that the old one worked and that this one isn't, or that neither of them worked, or wherever we might be with this. Okay, so there's a little PSA before we get started. All right, so last time we were talking about the one way between groups ANOVA. A little preview before we actually go through this material. On the exam, your final exam here, you will have one singular calculation question. It will be a one-way between groups ANOVA. So to that end, what I'm going to show you in the next two lectures on within subjects designs and then factorial designs and interactions, you will see material from this on the final exam, but it will not be part of a calculation. The only time you'll be asked to do a calculation on this type of work is as part of the homework itself, and the homework's already posted. So as a refresher of where we're at and where we're going, again, I suppose before we even start this lecture, the final exam, we're going to do it at home. You'll have a full 24-hour period to do it. I'll post it one day. You post it back to me the next day. Feel free to use notes, book, anything you want to do for that. You are also allowed to opt out of that final exam if you'd like to. The way we're going to do this, however, is that you're either going to take all four exams, period, like we planned, or you're going to drop one singular exam. Whichever exam you want to drop, whether it's the last one or one of your earlier three exams, you may drop, and then we will use the average of the remaining three exams which you have taken to substitute in for that one particular missing grade. Hopefully that makes sense. So if you want to skip the fourth exam because you've done so well on the previous three, that's fine. If you did poorly on exam 2 or 3 and you'd like to replace one of those exams, then do really well on exam 4, and we'll use the average to replace that. So hopefully everybody's good there. Also, all homework is already posted. It's not due until the final day of class. Okay. I don't know off the top of my head right at this moment when that is. It's April something. But whatever day we would normally have met in class on the last day, that is now when your homework is due. And it's just due by midnight that night. I'm not worried about it because we're going to also try and get our exam done in that short period of time. So I think that's all the announcements I have for you guys before we get started here. Let's talk about the one way within groups ANOVA. The first video here, I'm really only going to mention to you basically how the within groups ANOVA differs from the between groups ANOVA, both in benefits as well as consequences, sort of drawbacks. And then in the next video, I'll show you an example of how to calculate it. And then at the very end of that video, we'll talk briefly about effect sizes, or a measure of how large an impact your independent variable had on your dependent variable. Okay, so what are these benefits of the between groups design? First of all, why do we even discuss the between groups design? Well, one good thing about a between groups design is that because you've got different people in different groups, they are literally, as it's oftentimes referred to, independent of one another. This means that there is no way that the behavior of one individual can affect the behavior of another individual because they're in completely different groups being administered different treatments or levels of that independent variable. This means when they're done with their participation, they're also done, and their behavior or exposure to an independent variable can't carry over or affect them in later stages of an experiment, right? Once they've given you their data, they're completely done. They don't need to be measured a second, third, fourth, fifth, or maybe even sixth time. And so to that end, it's oftentimes faster, as long as you've got the participants, to be able to run a between groups design, especially when you can run them in groups. So imagine a situation where you need to run let's say 60 individuals through an experimental design. If you can split them in half and run 30 in one particular setting at once, and then run the other 30 at once, or maybe even at the same time with two experimenters, you could potentially get a tremendous amount of data collected in an incredibly short amount of time. Now, this does require multiple experimenters in that kind of case. It does require the sort of experimental design that allows for group testing, as well as the access to participants that allows that. And that may be, in fact, one of the sort of inherent flaws that sometimes in between groups design as well. It can be what we might say, I guess, generally speaking, more costly, right? And so the sort of flip side of that coin, the benefit of the within groups design is that it's less costly. So what do I mean by costly? Well, first there's the direct financial implication of costly, right? Participants cost money, right? They either cost indirect money insofar as the subject pool gives people credit towards their intro psych class, right? We're compensating you for your time in the experiment that you took place in. And other experiments actually will pay you cash, right? And so I don't remember if I told you guys or I told my cognition class, there are frequently research studies being done at Ann Arbor and other, especially larger campuses with more neuro equipment available, that pay participants to sit through one of these studies. Studies can sometimes be an hour, maybe longer. And in an EEG study, you have to wear a cap that sometimes has this gel squirted into it that can sometimes make your hair a little bit sticky until you take a shower. And so, because of these sorts of consequences, these drawbacks that you have to deal with as a participant, they'll pay you sometimes $100, $200 an hour. So now let's go back to that between subjects design. Imagine now, because you've got two separate conditions, a caffeine and a no caffeine group, right? Or people that eat chocolate cake versus people that eat lemon cake, right? That distinctive difference now is going to require different individuals in different groups for between subjects design. So in order to hit your central limit theorem level of participants, where we know we've got that normalized distribution for comparison, we need about 30 people, right? 30 observations, but that's in each of those groups. And so in order to have a between groups design with just two levels, just two groups, you're looking at probably around 60 participants that you have to collect data from. Now, imagine a different situation, however, where it's a within groups design, where I take my cake example and I'm seeing whether there are differences in preference for one cake versus another, and I have everybody eat the lemon cake first. And then after a good period of time where they're no longer still full, right, from the previous piece of cake, they no longer still have that flavor in their mouth, then they try the other piece of cake. Now I've got the same 30 individuals being measured two different times. Although it may take me physically more time in a single session with each of them, I've only had to recruit 30 participants instead of 60. Do the math now. If this were an EEG study and we were doing $100 an hour or $100 per half hour with a participant, this can literally save you a ton of money to do it within groups design. It can, just like between groups can sometimes be faster, within groups can sometimes be faster for this reason, because there are fewer individuals you have to collect data from. You can sometimes collect the data even more quickly. So again, there's different pros and cons to each of these two designs. That doesn't really make one of them beneficial to another in any particular way, insofar as you'd always be able to say that's the best design to choose regardless of the experiment. It's really the particulars of the study that dictate the design that fits it best. Another cool thing, and this is sort of both a conceptual and mathematical thing that occurs in between group studies. Remember, we talked about how if you've got a group of individuals, right? Let's say there's a group of them that get caffeine and a group that don't get caffeine. And we talk about these sort of distributions that spread out. The distribution is representing how not everybody in a singular group performs exactly the same, right? Some will be up at one end of the distribution, some will be up at the other end of the distribution, and many will be sort of the middle. That's variability. Um, we have that within groups as well, right? And so you still have a group of individuals, and they still will vary from one another. But in a between groups design, because each group is different people, there's different amounts of variability in each of these groups. Even if they're approximately equal, there's no way of tracking that variability from one group to another because it's not the same individual. But if we have within groups designs, then the same groups, this A, B, C, D, E that you see on the board, is measured time 1, time 2, and time 3. So then let's imagine that this was something like cake, right? And we were trying lemon cake versus chocolate cake or something. If one person has very, very poor taste sensitivity, right, they might find that both the lemon cake and the chocolate cake are fairly weak, and they're going to rate them both at flavor scale pretty low on the scale. And that's largely due to their idiosyncratic difference in being a sort of low sensitive taster. Because we measure that same person at multiple time points through the experiment, we can now see how that individual's differences, their variability, performs in one setting and then track it to the next setting and the next setting. The real win there is because it's the same individual and the same variability, we can remove that variability. Variability really in some ways can be thought of as error. So removing that out may allow us then to see our actual effects a little bit more clearly. When do we use within subjects design? So all the time, and this is by no means an exhaustive list, but things you might be at least somewhat familiar with to sort of see how a within subject design really is at play here. So taste testing. You may have never been a part of a taste test. I ran a beer club for a while in grad school, so we had beer tastings, right? We would do beer taste tests. And what we would do is we'd have several beers. We usually didn't know what they were, right? So like these individuals in the top left here being blindfolded. And you'd sample the beer, and you'd maybe make some notes, give it an overall rating for how you liked it. And then you'd rinse out with water and you'd sample another beer. You'd rinse out with water, you'd sample another beer until you'd sampled all of them and you'd made a note on all of them. Now we then could look at it because we were dorky graduate students in my club and figure out which data supported which beer being the best. But what I'm trying to point out, though, is that each individual in that club, in that group, tried every one of those individual beers. Each person in a taste testing is likely to try the taco, the burger with shrimp, the burger with egg, the burger with whatever, all the variations that that company is trying to market. And so you're being exposed to every level of an independent variable and being measured once and twice and three and four and five and six times, depending on how many variations there are in the food you're eating. We see this at the battle of the bands. Right, one band gets up there, they play really hard. Another band gets up there and they play really hard. Another band gets up there and they play really hard. You've got all three of these bands now. Which one's going to win? The audience has now been exposed to all three levels. They've been exposed to each type of band, each different variation of band, and then they get measured by sometimes how loudly they applaud. Right, and if you hear lots and lots of screaming for band one, then you mark that down. And less screaming for band two, and then even less screaming for band three. Well, then band one wins. Right? It's a very not quantitative way of doing the same thing we try and do in objective research. The one you might be a little bit more familiar with, as far as something that we do a lot in research that you've probably read, is longitudinal research. Right? And so longitudinal research can track somebody over a longer period of their life. It could be something as short as a couple of weeks or a month. It could be something longer as years, even decades of their life. And so you might study somebody as a baby just to see what sorts of things we can measure about them. And then see, when we study them again at age 8, how much of what we knew at age 3 predicts what we see at age 8. And then follow them again to age 15 and 25 and 35 and 45, 55, right? And then you can track their individual performance as well as the overall effect of aging and the effect of society on aging, right? They're going to respond uniquely different. And because you can see it at each of those time points, you can measure that variability. That variability is really not about your independent variable. It's about how they're a unique person. And you take that out because in research, we don't want you to be a unique person. We want everybody to be identical clones, and then we want to see how this particular independent variable works. Because you're not clones and everybody acts differently, the within subjects design allows us to identify that idiosyncratic difference and then remove it. That really ends up being, from a statistical standpoint, a huge win to this design. That being said, there are certainly drawbacks. Right? As I said, you're not going to ever say that the within versus the between is always the best design. It has to be as a function of the study itself. So order effects, right? And so this graphic here is obviously joking around, but imagine if you were in a chili cook-off or a cake tasting or any of these sorts of situations. This happened to us frequently with the beer tastings. Every now and again, when people wouldn't think properly about the order in which you had the beers, you might have a beer very early on that has a super high alcohol content or is incredibly tart, right? And after trying one of those beers, it modifies either your perception because of the alcohol, or it modifies the way your taste is sensitive to other flavors following that because of the particular flavor compounds you had in that beer. Same thing might be happening here in this joke comic, right? They're in this joke comic here. The taste test goes through. Unfortunately, the first taste killed him. Because he's now dead, his rating of the third, fourth, fifth, sixth, and sixth drinks or foods is going to be relatively low. But it's not because those individual drinks actually are crappy or because those foods actually taste bad. It's because the effect of the first one has now carried over into the following levels, right? Him dying, me drinking something with too much alcohol or too sour or something like that is going to change the way I perceive things in such a way that subsequent exposures are going to be affected by that. They're going to be carried over into that. Sometimes it's just the bleed over effect. Other times it's just a matter of order. If I want to know whether you're better or worse at solving a particular puzzle, if I let you watch a video, there's only so many times I can do that back and forth, right? So if I let you solve a puzzle and you spend a little bit of time solving it, and then I say, okay, now we're going to do it again, but I'm going to show you the video, and then I'm going to give you the puzzle. You've already solved the puzzle once. The video might help, but it's unlikely to help any more so after you've already solved it, right? And so that order effect can occur as well. We also have, frankly, practice effects and fatigue effects. There are some tasks that once you've done them a second time or a third time, you will simply be faster or better at doing them. If that's the case, then it's not really a function of whatever was being manipulated between the first time and the second time. And instead, it's merely a function of the fact that you did it twice, you did it 3 times. I've also had studies before, and there's a myriad out there, that simply take a while. And fMRI studies tend to take a while because there's multiple blocks of presenting stimuli, there's multiple blocks of recording responses, and frequently by the last few blocks in an fMRI study or in any longer study, any physically exercising or taxing study, that you begin to feel tired. Sometimes physically fatigued, sometimes mentally fatigued. And in either of these cases, those fatigue effects can then affect the performance of the latter measurements. Right? And so again, all of these things can only happen within groups design because you're measuring people multiple times, right? You can't have that happen between groups design because they're completely different people experiencing these things. What do we do then? Do we have to give up on within groups design? If we're worried about something like order effects or even practice or fatigue effects, one thing we can do is what's called counterbalancing. So if you look at the graphic there, and I apologize if my video is blocking it a little bit, we say we've got group one and group two. Let's pre-test them on some ability, maybe vocabulary, right? Then we give one group treatment A, say it's a vocabulary building video, and then we test their vocabulary. And then after they get that one, we give them a vocabulary building homework that they have to do, and then we test their vocabulary. Well, what if there's an order effect? What if watching the video affects them in such a way that later on, when they do the homework, they're still affected by it? They have a carryover effect. Well, in order to rule that out, for group two, we reverse the order of those two tests, those two tasks. We now do the homework with the practice or with the vocabulary test, and then we do the video with the vocabulary test. This counterbalancing allows you then to average over the two conditions of the two cases where they've been given the homework and the two cases where they've been given the video. And this, excuse me, removes the effect of order, right? So counterbalancing can be really helpful. And you see when it's really easy like this, where you only have two different measurements, and you have to counterbalance two different measurements, you really only need two different groups. One group that gets measurement A, then measurement B. The other group gets measurement B, then measurement A. What happens, though, when your independent variable has more than two levels? When instead of just measuring at time one and time two, instead of just measuring how a video affects it and how a homework assignment affects it, what if it was a video, a homework assignment, some flashcards, and a game we played? We had four of those. What if we had six of those? Again, the more conditions you have, the more rows or the more different ways you'll have to reorganize them in order to counterbalance them. So if you look at this example here, if we had three conditions, so just three levels to an independent variable, right? Something like no caffeine at all, a tiny bit of caffeine, and a lot of caffeine. Well, in order to counterbalance for all possible orders, you calculate that by having the number of levels factorial, right? Factorial is that exclamation point. So 3 factorial would be 3 times 2 times 1. So 6 different orders have to be created in order to handle an independent variable with just 3 levels, 3 conditions. You can do the math real fast. What if you had an IV that had more levels? What if it had 4? Just 4 levels, just an additional level from the previous example. You now, instead of 6 orders, need 24 orders to account for all of that. That can become a logistical nightmare because you have to keep track of participants going through 24 different orders of your experiment, right? In order to handle this, one way that we can solve the problem of making sure that our conditions experience enough counterbalancing to rule out order effects, fatigue effects, practice effects, carryover effects, any other ones that I didn't mention, we introduce what's called a Latin square design. Okay, a Latin square design is a really cool technique that essentially moves around each of the positions so that they occur in an equal number of times in each row and an equal number of times in each column. Let me show you what I mean here. Not in the stained glass to the side here, which was put in a church, I believe, in England to commemorate the beauty of the Latin square design. That's how awesome dorks can be. But if you look at the graphic below the paragraph here, so if we say that it's an arrangement of X treatment levels, so on the top left of that square, we have the situation where we had 3 treatment levels, A, a B, and a C. Each one gets to be repeated then X times, so each level is going to be repeated 3 times. You'll have 3 occurrences of A, 3 of B, 3 of C, but they're repeated in such a way that each treatment or level appears exactly 1 time in each row and 1 time in each column. So if you think about the columns as the order they do them in, then in the first row, that participant or that group of participants will do task 1, task 2, and then task 3. In the next row, however, those participants will do them in a different order. They will start with task 2, then they will do task 3, then they will do task 1, and then finally the last row down there, that group of participants would start with 3, go to 1, and end in 2. Notice then that task 1, occurs first for one group, third for another group, second for another group. Same is the case for each of the other two levels, such that they only occur once in each row, once in each column. So you can see it graphically filled out below, or what it would look like if you had 4 treatment levels. Either way, the lattice grid design allows us now, so if you look at the top right, to handle a 4-level independent variable with, instead of 24 rows, just 4 rows. That can be a massive win in an experiment that's got sort of complicated independent variables. So something to keep in mind.